We've got this problem. It's from chapter 21, problem 35. I don't know. The figure in the textbook online is 21.50. My book has it as 21.52. So I don't know. Whatever you guys, it's in problem 35, chapter 21. Same picture, okay? So all the resistances are the same, all the EMFs are the same. Now, hopefully by now you've seen the video on terminal voltage versus EMF voltage, because I'm not going to go through that in this at this point. I'm also not going to do Kirchhoff's rules, but Kirchhoff's rules definitely apply. And we have two. We have one, we have the junction rule. Which is based on the conservation of charge. Okay, and then we have the second rule, which is the loop rule. And that is based on conservation of energy. Okay, so we're going to apply those rules. Now, in the picture, in the figure, they label for us a current going this direction, I2, across the middle. So going from A to E, straight through the middle, we've got I2. They've also labeled for us in this direction, going up the side here, I3. So that means I3, I'll do it in blue here. I3, I is going to be going like this from E to A through those, whatever those components are. And then they have one last current, the only current going through this third wire, and that's I1. Okay, and that's going from A to E around the top side of the loop. So we've got three currents, and we don't know what they are. And basically that's the question. And so Kirchhoff, he went through and figured out how to do these things in a good way, and we're going to take advantage of Kirchhoff's work. So here we go. Let's apply first the junction rule. Junction rule is easy, okay? Everybody loves the junction rule. You apply the junction rule and you're done once. So how do I want to do it? So we're going to get equations, all right? The whole point is so that we can look at this figure and come up with equations. So equation 1. Excuse me. I'm going to circle the equations 1, 2, 3, and 4 so that everybody sees when I go to work with equation 1, I'm working with equation 1. Okay, and you'll see it circled 1. All right, so there's that. So equation 1 is if we go to point A here, and we look at all the current going into point A, so the only one going in, if you look closely, is I3. So I3 is going in, and that has to equal all the ones going out. So I1 is leaving A, and I2 is leaving A. So we could say I1 plus I2. Now you can do the same thing for the point E. And on point E, we have I1 going into it, we have I2 going into it, and I3 coming out. So I1 plus I2 is equal to I3. So either way, you're going to get this equation 1. Okay, so we've got one equation. We're going to use it in a minute. Now we have to start applying the loop rule. We're going to get equations for the loop rules. The loop rule is a little bit more difficult to apply, all right? So here we go. You first have to say what is your loop and the direction for what your loop is going to do. So in this first top half, I'm going to say this is loop 1, and I'm going to start, it doesn't matter. We can start at E2, EMF 2, and we can go all the way back around to EMF 2. So we'll start here, and we'll go all the way back around. Okay, so that's our loop 1, all right? And then for the loop 2, I'm going to do the same thing. I'm going to start at EMF 2, and I'm going to go all the way around the circle like that. Okay, so one I'm going counterclockwise, the other one I'm going clockwise, but you'll see why in a second. It's because EMF 2 is the largest EMF, and I want it to always be positive. It'll end up helping me be positive with a lot of things, and I'd rather have positive signs than negative signs. There's one other loop, okay, and you can always do this one if you want to, and that's loop 3, and you could do it however you want. So you could start at, I don't know, what's the biggest outside EMF? E1, E3, or E4? E4 is the biggest, and if we started at E4 and went all the way around like this, that would work too. Okay, so there's another equation that you can have. We don't need all 4 equations because we're going to get an equation from the junction rule. We're going to get equation 2 from loop 1. And we're going to get equation 3 from loop 2. And that ought to do it for us. We have 3 unknowns. All the other things are known. So 3 equations, 3 unknowns. You don't want any more than that. It just mucks up your system. Okay, so I don't have enough room right here to... so essentially we're going to go back and forth, up and down on this page to get our loop equations done properly. So we already have one equation done. We can do this. And now I'm going to work on the equation for loop 1, which is equation 2. And I'll just do a little 2 here. And it's going to be long, all right? So equation 2 is going to be long. And just bear with me as we figure it out. So what did I say I was going to do? I'm going to start at E2 and work my way around. So the whole thing, when you start at one point and you end up back at that other same point because you're using conservation of energy, you're adding and subtracting. If you go from one point to another, but it's the same point, you should always end up with 0. So we're going to end up with 0. Okay, and we're starting at epsilon 2, our EMF 2, all right? And then we're going in the same direction as my loop, right? And the current I2 is going across R2 in the same direction. That means I have to use a minus sign. Okay, why is that? No, do I want to talk about why? No, I've already told you guys how to do Kirchhoff's rules. So we're in line with the current. That means it's going to be negative. Okay, it's a voltage drop. So I'm going to put I2, R2. The next thing is we're going to do the same thing, but we're crossing R2, big R2. So I'm going to subtract off I2, big R2. now we're going to turn the corner, go up towards I5, but in our case, I5, is it going with our circle or against it? I1 is going against it. So we are actually going upstream. So we're going to put plus I1 times R5. We're going to put plus I1 times R1. And we're going to subtract, because we're going from positive to negative on epsilon 1, we're going to subtract epsilon 1. Then we're going to get to big R1, I1, big R1. And again, we're going against the grain. We're going against it. So we have to add. We're going upstream. So this isn't a voltage drop. It's a voltage increase. I1 times big R1. And we make the left turn at A in Albuquerque, and we get back to E2, and we've done our loop, and that means we've got 0 again. So that's the first loop equation, which is equation 2. And I'm going to do equation 3 here, and then we can slide up because we don't need that picture anymore. Once we've done these things, we don't need the picture anymore. And then I'll slide up and do the algebra. We can always come back up to the top and get our values later as well. So I've written out here this equation 2, loop 2, I've got 0 equals, and then again, we're starting with epsilon 2. Let's move up a little bit. Okay, so we're starting at epsilon 2. We're going to go all the way around and get back to epsilon 2. So epsilon 2. Now, I'm going to subtract off the I2, R2, not R2, D2. Okay, and then we're going to subtract off I2, big R2. Then I3 happens to be going in line across R4 as well, the little R4. So I have to subtract off I3 times R4, little R4. And we get to E4. Now E4, we're going positive to negative. So I have to subtract off our EMF 4. Then we go down a little bit further. We get to minus I3, R3. And we're now getting a boost in voltage. So we're going to have to add in, because we go from minus to positive on our battery, our EMF 3. So we're going to plus EMF 3. Make sure I have that right. Okay, yeah, good. And then that ought to do it. We're back around. Nope, we've got one other resistor. This one, I didn't name it yet. R3. Do I have a value for R3? Ooh. Do I have a value for R3? Yeah, okay, good. R3 right there, 78 ohms. Okay, so we have one last thing to put in here. We're going along with I3, so we have to subtract off I3 times R3. Okay, and then we get to Albuquerque and take a right. Okay, so good. Now, fabulous. Now all we have to do is rewrite these things and start putting them in a nice form so that we can work with it. Now, algebra is algebra, and it's not always easy or pretty or whatever. But once you break it down and get all the stuff, you should be able to do it. I'm not going to go through what loop 3 is. It doesn't matter. You can do it if you want, but I'm not doing it because it's just a waste of time. We've got what we need. So let's continue. We've got our 3 equations. All right, so let's rewrite equation 2. Straighten it out a little bit. So equation 2 is 0 equals epsilon 2. Let's put all the epsilons together, all our EMFs together. So we've got epsilon 2 minus epsilon 1, and EMF 2 minus EMF 1. All the I2s we can put together. So we're going to subtract off all the I2s times whatever they're multiplied by. So there's the little r2 plus big R2. And we're going to do the same for the I1. And they're all positive. So I like the positive situation. Let's keep it positive. So let's do I1. And then we'll put in all the resistances, R1, R5, and big R1. Okay, so there's equation 2. Here's equation 3. And don't forget we've got equation 1 here. Okay, let's rewrite equation 3. We've got 0. That equals epsilon 2, and we're going to subtract off epsilon 4, but we're going to add epsilon 3. All those are numbers, okay? So that's going to be nice. In a second, we can just go in and plug in what all those numbers are. Let's deal next with our currents. We're subtracting off I2. And I2 has R2, little r2, plus big R2. And then we can do the I3s. All the I3s are negative, so we're going to say I3 minus I3, and then we're going to multiply by R3, little r3 plus big R3 plus little r4. Do I have that right? Okay, here's little r4, here's big R3, and there's little r3. I've got little r2, big R2, and that's there, and then I've got this, this, and this. Okay, good. We got everything from there, and we can start putting in numbers for these. So let's redo number 2. 0 equals E2 minus E1. What is E2? Okay, so I don't know. Let's do a screenshot of this. I have it written down on a piece of paper right here to my right. So once we start putting in these values, we're going to get an easier time of it, because we really don't want to deal with all the variables. I know most of the time I want you guys to do work with the variables, but in this case, it's just too cumbersome. So we can cut out a lot of these variables just by putting the numbers in. So that's what we're going to do. So E2 minus E1. So what's E2? 48 minus E1 is 24. That leaves us with 24 volts. Okay, and you know what? I'm not even going to put... okay, I'll keep the units. I kept the units in my notes. I may as well keep them. Let's keep the units. All right. Now, we're going to subtract off R2 plus big R2, and that means 40 plus 0.5. So we've got 40.5 times I2. And then we're going to add R1, big R1, so that's 5.1 plus R5, that's 25.1 ohms. Do I want ohms in there? I suppose. We should probably keep our units. Until we actually multiply these things together, we really don't have volts. I don't know. It's up to you guys. I'm going to keep them. All right, let's do number 3. We've got 0. E2 minus E4 plus E3. So 12. E2 minus E4 is 12 plus E3 is 6. That leaves us with 18 volts. Did I do that right? I want to make sure I'm doing that right. E2. Yeah, I think that's right. Okay. And then I'm subtracting off R2 plus big R2. That's 40.5. 40.5 ohms times I2. And I'm subtracting off again R3, big R3, and R4. So R3, little R3, is 0.05. All right. Big R3 is 78. And then little R4 is 0.2. So we end up with 78.25 ohms times I3. So that's a nicer way to work with it. I know it's just work with the numbers at this point. It's okay. So now we've got these things. All right. Wait, did I put an I3? You guys are probably screaming, change it to I3. Change it to I1, I mean. That's not I3. Sorry, you're right. It's this I1 that I want there. So I need that I1. So there it is. Okay, so we've got I1, we've got I2, and then we've got some voltage. We've got I2, and we've got I3, and then we've got some voltage. So what we can do is we can use the fact that I3 is equal to I1 plus I2 and start solving for I1 and I2 and so on and so forth. Okay, so why don't we, how did I do it? Let's see, what did I do? I wanted to use that equation. So I used equation number 2 and I solved for I2. So let's just do that. So let's use equation number 2 and solve for I2. Then I'm going to take I2 and substitute it into every place that I2 is in the third equation. That's it. That's all we're doing. But, you know, you guys are probably not used to doing this a whole hundreds of times. Nobody likes to do this. In fact, computers do it now for us so easily that we just run programs that will do these things for us, and we don't have to do it by hand. However, knowing how to do things by hand helps you understand if you need to program them later or whatever. You understand what is actually happening. The mechanics of the whole situation. So that's the whole point. So let's solve for I2. Not terribly difficult. I'm taking equation 2. Since 40.5 times I2 is negative, I'm going to put 40.5 times I2 on one side of the equation because the other side of the equation is 0. So I'm just adding to both sides. And that leaves me with 24 volts plus 25.1 ohms times I1. Now, the next step, of course, is divide out the 40.5 ohms. And we end up with 24 volts plus 25.1 ohms times I1. And we're going to divide that by 40.5 ohms. All right, so we know what I2 is. We don't know exactly what I2 is, but we definitely have a handle on it, equation-wise. And we can step forward now. Let's rewrite equation 3. Equation 3. So I'm going to rewrite it. It's 18 volts minus. Now, every time I see an I2, I'm going to put in 24 volts, 25.1 times I1 over 40.5. So gross, I know, but that's what we're doing. Now, here's the nice part. We've got 40.5 times I2. Well, 40.5 in the denominator and the numerator is going to cancel. So really, on this first term, I'm going to get 24 volts. So minus 24 volts plus 25.1 ohms times I1. And you guys hopefully see that the 40.5 cancels out, numerator, denominator. I want to make sure that I get the negative sign passed through correctly. So that's why I put parentheses around them, and it'll come back to haunt you if you don't have, if this positive sign doesn't end up being negative when it's all over, that will haunt you. Okay, so you got to make sure that that works right. Now, we've got 78.25 ohms, but it's times I3. But we already know I3 is I1 plus I2, so I1. But instead of I2, I'm going to write 24 volts plus 25.1 ohms times I1, all divided by 40.5 ohms. All right, that's going to give us an I1, and we can, once we've got I1, we're good. Let's simplify this a little bit. We're not to the point of actually throwing things around. We're going to take our 18 volts. We're going to subtract off 24 volts. We're going to subtract off our 25.1 ohms times I1. We're going to subtract off 78.25 ohms times I1. We're going to subtract off 78.25 over 40.5 ohms. They're both ohms. And we're going to be multiplying that by both 24 volts and 25.1 ohms times I1. Do we need more space? Yeah. Okay. So we're getting better. We're getting there. We're doing a little bit better. We can, this is going to end up, these two guys are going to end up giving us negative 6 volts on this side of the equation. So what if we wrote 6 volts on the other side of the equation? I don't know, just to do it. And that means that we've got minus, I'm just still rewriting, minus I1 times 25.1 ohms minus 78.25 ohms times I1 minus, this is a ratio. Okay, you could go into your calculator and figure out what that ratio is real fast. If you want to eliminate that ratio, should we do that? and I'm not showing that little 40.5 there. I want to have 40.5. Let's okay. Sorry, I'm trying to go through and do a little bit of calculations on my calculator, and I've got two calculators, and one's RPN and the other one isn't, and so it takes, my brain doesn't want to do both. Okay, so 1.93, I'm going to just stick with 1.93 for that ratio, okay? And I'm going to do 1.93 times 24 volts. And then I'm going to subtract 1.93 times 25.1 ohms times I1. All right, well, it looks like we've chosen I1 to go in the wrong direction because every single thing here is negative, but we know we've got positive on the other side. So that means that I1 is going to show up as a negative, and that also means that when we didn't choose it, you didn't choose it, I didn't choose it, the book chose it, but when they drew I1 going in that direction, this direction right here, now let's do it in blue. This direction for I1 is wrong, and that's okay. The way you're supposed to do Kirchhoff rule problems is you draw out what you think or what you expect, or not even that. You just draw it one way or the other. It doesn't matter if you think or expect it to be that way. If you end up with a negative, then you did it backwards. You drew the current backwards. So the current actually goes the opposite direction, and you may not have, you'd be like, what? I didn't see that yet. But yeah, come back down to this equation. Notice that all the terms are negative. So that means that it has to be a negative. Okay? We'll see hopefully in a minute. Do they all have to be negative? Yeah, they all have to be negative. Okay, so let's handle this bit first. And by this bit, I mean this one right here. Because I want that 24 volts times 1.93. So I'm going to multiply by 24. See what that is. That's 46. So we're subtracting off 46.37 volts here. All right. But I'm not going to subtract off 46.37 volts there. I want to add them to the other side. So I'm going to add 6 volts to that. And I'll get 52.37. So on one side, I've got 52.37 volts. And that equals all the other stuff on the other side. And now we can do a few other things. Okay, wait. Before we continue, 1.93. 1.93 times 25.1, that's 48.44, 48.44 ohms times I1. And that's negative as well. Okay, so I think we've got everything we need. We've got our 52.37 on one side. We've got I1. All of them are negative. And we're going to take 25.1. We're going to add it to 78.25. And add it to 48.44. So I'm going to add 25.1. And I'm going to add 78.25, 78.25. That's 151.79. 151.79 ohms. And so far so good. We'll bump up here a little bit. And we'll solve for I1. I1 equals negative 52.37 divided by 151.79. They're both, this is volts and this is ohms. So volts divided by ohms is amps. And so we're going to end up with whatever that is. Okay, so I got 151.79. I'm going to flip that. 1 over that, and I'm going to multiply that times 52.37. 0.345. 0, don't forget your negative sign. 0.345 negative is equal to I1. Okay, whew. Everybody goes, whew. All right, now we can then pretty simply go back to our work at this point. Okay, we can very simply go back into that equation right there. It's the easiest one to work with, and put in our 0.345 negative, and we'll get our I2. Okay, so let's work with that. I'll slide back up a little bit here. So I2, do I want to do it in, I don't. I want to do it in black. All right, I2 is equal to 24 volts plus 25.1 ohms times minus 0.345 divided by 40.5. So what does that equal? Let's just do a little 24. Now, that's a bad place to start. When you have RPN calculator, you can do that start, but I can't. So 25.1, we're going to multiply that by 0.345, but it's negative. And then now I'm going to add the 24 volts plus 24. That equals 15.34, and I'm going to divide that by 40.5. Divide by 40.5. So that gives me 0.378, 777, whatever. We could do 3788 if you want. Oh, don't forget your units. We've got amps here, amps there, and that equals I2. Well, we're almost home, guys, because why? We have one last thing, and I remember what it is. I1 plus I2 equals I3, and that was pretty easy. So if I1 plus I2, is that right? I1 plus I2 equals I3, yes. Okay, good. So now we just have to say that I3 is equal to 0.3788 amps minus 0.345 amps. And that means that I3 is equal to, let's subtract off 0.345. And I3 is 0.03378 amps. And there are your answers. And you can plug those in and move on to the next problem. Okay, good job, guys.